across the problem of how do we characterize an application. And the application characterization revolves around, first of all, some kind of a traffic model. What kind of traffic does a particular application generate? And so you think, for example, at just two different types of traffic. Let's say making an ordinary phone call. In an ordinary phone call, the traffic while you are talking from the sender to the receiver is at a fairly constant rate. There are interruptions, of course, between syllables when you pause to think about something, but generally you get a fairly constant data stream from sender to receiver. But then at some point you stop talking and you start listening, in which case the channel from your side to the other side is basically empty. And so the channel now in the opposite direction is filled in the same kind of way with the same type of traffic. So this is one model. On the other hand, let's say you're sending an email. Now it's a completely different model. First of all, the traffic is all in one direction. And secondly, when you hit the send button, the traffic goes out at a constant speed. It might be packetized in some way into chunks of bits, but there is a kind of a continuum until the message has been sent and then the connection goes down. So it's a completely different kind of traffic model. And there are many other applications where the traffic is sort of half duplex, or the traffic is simplex, or the traffic is full duplex. That is to say, both sides talk at the same time, or only one side talks forever, or ever, the other side never responds, or there is a half duplex where you talk for a while and then you listen for a while, and the other side talks. So there are these different kinds of traffic models. And over the years, various organizations have developed specific models, probabilistic models, that characterize the different types of traffic that you have. For example, most communications nowadays is conducted in a so-called packet-switched mode, which means that the information you transmit is cut up into chunks and called packets, and then there may be a packet transmitted now, and then a little bit later another packet gets transmitted, but in between those two packets, other people may use the same channel that you are using to transmit their packet. So there is, in other words, a statistical distribution of your packets relative to time, and this distribution depends a lot on the application, and it depends a lot on how many other people are active on the same channel as you. So there's a channel sharing problem here, and that creates now the need to develop models for how traffic from different sources interacts or mixes up with traffic from other sources. So there's, in other words, now a whole theory here of developing traffic models that describe the amount of traffic that's generated by the different applications, and then matches the capacity of the wireless network to the needs of these particular kinds of traffic models or applications. So this is what we want to look at now a little bit, to find out what kind of traffic models exist, and then ultimately use these traffic models to analyze things like throughput of particular types of wireless networks, such as the ones that I discussed a minute ago. So this is what we will do as a next step. Now, as I mentioned before, the slides that you see here are all available on Blackboard, so you can pull them out anytime you want to and rehearse them, review them. But I will just project several slides, several sections of the slides for each particular lecture. And right now we're going to start talking about telecommunications traffic models. So why do we need to know what the traffic levels are, or what kind of traffic we will have over a particular wireless network. Well, it's obvious because a wireless network or a wireless channel, if we just go down to the channel level, has a certain bandwidth. And this bandwidth puts certain limits on how much data you can get through in a particular period of time. So there is a need now to try to match the bandwidth to the traffic of the application or vice versa. And so we need to know something about the particular kinds of traffic levels that we experience for particular applications. So now there are a number of issues that we have to consider. For example, there is network optimization. If we have a limited amount of bandwidth, then we might allocate that bandwidth to different applications in accordance with the requirements of their traffic. And in this way, we can do an optimum allocation of bandwidth to a particular application. So let's say I have a bandwidth of a megahertz, and I have 5 different applications, and one requires a throughput of 10 kilobits per second, or let's say 10 kilohertz of bandwidth, and another one requires a throughput of 500 kilobits per second, or half a megabit of bandwidth. So I can divvy it up in such a way as to optimally use my available bandwidth and divide it up into the particular applications in accordance with their needs, in accordance with their particular traffic levels. So this is how we might have a relationship between traffic levels and how to optimize our network resources. Congestion control and flow control procedures. If we know something about traffic peaks, for example, of particular applications, we can organize the available resources in such a way that we have a low probability of getting into a congestion situation where suddenly several applications are transmitting at peak data rate and cause congestion and cause a blockage of the network. We also want to know something about traffic levels when we do network simulation and modeling and network administration, assigning different bandwidths to different applications. Capacity planning. If we know what traffic levels to expect, we can say, well, we need more bandwidth or we need additional resources on the transmission side and on the receiving side. So we generally need to know something about the traffic in order to really implement a network technology that is responsive to the particular demands of the different applications. All right, it is now 7 o'clock, so let's take a 10-minute break, and then we will continue on the idea of how to characterize the traffic levels in not just in wireless networks, but in a general sense. See you in 10 minutes. then that service, of course, requires a certain capacity from the system. And so the service then, the demand for service on the system is going to be the product of the number of service requests that you get onto the system and the duration of a particular service over a period of time. Okay. Now, if we look at the service duration itself, we realize that it really has three components to it. One is, first of all, the time that you need to spend on the system to actually get connectivity to the receiver, the dial-up time, if you like. Then there is the time to actually transfer your information from sender to receiver. And ultimately, there's going to be a time to free yourself again from the service, to disconnect, in other words. And for voice traffic, that's pretty obvious. From the time you pick up the phone, you get a dial tone, you dial in your phone number, and all this time is the service request time, or the connect time. And then the phone rings on the other side, and the other side answers, and now you still have not transmitted a bit of information. And then, of course, you do your talking, and so by the time you hang up, you have the particular use time, and then the total time of hanging up, together with the time to dial up in the first place, and the time you spend talking, constitutes the total, the duration of the service. Okay. Now, if we look at the traffic load then altogether on the system, okay, it's clear that it's going to be the product of the number of requests you have in a particular period of time, okay, and the duration of each such service. So you might have 10 requests for service inside of an hour, and each request for service on average lasts 2 minutes. So you have 20 minutes of service in an hour, and of course the traffic load would be 0.2. 20 minutes of service in an hour is 20 over 60, so a third would be the traffic load, right? So this is the simple idea of coming to grips with load factors on a particular network. Okay. Now, of course, when you look at the details of how traffic is generated, or traffic demands are generated, then you can see that it's very statistical in a sense, right? Think about a telephone number, a telephone company access point, a central office in the telephone network, and monitor what this central office sees. Every time someone picks up the phone, it constitutes a service request. And so these phone requests, these phone call requests, come in at random times. So there may be now a time period where there is very little demand, for example, in the middle of the night, and then there is a time period when there is a lot of demand in the middle of a working day. So we have the number of requests for service then is randomly fluctuating and depends, of course, on things like the time of day. It depends on events that occur. For example, in an emergency situation, a lot of people make phone calls. So it may also depend on the state of the network. If this network is very good, it attracts a lot of service requests. If the network is terrible in terms of performance, it may attract very few. So now we need some statistical parameters to measure these service requests. And so these parameters then basically form a random process. And the random process then describes, in a way, the occurrence of service requests in time and how long each particular service request lasts. So these particular components or parameters of the service request numbers or occurrences and the service durations, the time duration associated with these service requests, these may also be particularly organized or related to the application you have, and they may be statistically independent from one application to the other, or they may not. So one application may generate a lot of service requests on another application. So there could be correlations between applications, the service requests for different applications, and the service durations of different applications as well. And so they may be statistically independent, and then again, they may not. Here's a picture that is used by telephone companies, for example, to describe their experience with telephone call requests. So you see here, for example, channel by channel occupation. There are these call arrival points in time. Here, a call arrival occurs here, another one occurs here, another one occurs here, and another one occurs here. And then there are the call holding times. Here is a call holding time for a particular call. And then there is the idea of getting blocked calls. When the system is completely saturated and a new call arrives, it gets blocked. And this is what happens in telephone calls when you pick up the phone and you don't hear dial tone. The reason you don't hear dial tone is because there's no capacity to connect your particular phone to make a service request really doable because of lack of capacity. And so if you look at the traffic volume now, you see these particular changes there in ups and downs. A new arrival, a new phone call arrives, and another phone call is completed. So the amount of traffic volume goes up and down in a statistical manner. So these models here are used by the phone companies to try to figure out how much capacity they need to service a particular application. And as you see in this example here, the peak capacity is here. And so they might design a system that can handle this peak capacity and possibly a little bit more. But the key point is that you need to know what this capacity is, how it varies over time, and so that you can now assign or develop or implement the amount of channel capacity to handle this traffic volume. Okay, now obviously traffic is unpredictable. It's totally random, and we need to have a probabilistic model for, let's say, computing or measuring the key parameters of these different types of traffics. So the traffic models then, they focus on particular parameters of the traffic. For example, the average load, the expected value of the load as a function of time. And as you can easily understand, if you look at the effective load on the telephone system in the middle of the night, it's different than in the middle of the day. And so these things are time varying, and so they in effect are a random process. And then you need to have a second quantity here, which is the bandwidth you need, or the amount of channel resources to handle that particular demand of service at a particular quality of service. That's the key point. You can transmit data at a megabit per second over a channel of 1 hertz if you don't give a darn about what comes out the other end, if the quality is of no interest to you. So everything has to be relative to the quality of service requirement of the particular application, the particular traffic model. And so if you have a good idea of the traffic model in terms of its statistical parameters, or even as a stochastic process, then of course the network designer can provide the right kind of capacity that delivers this particular level of service according to the traffic models. And now there are a number of such traffic models that are focused on single applications. For example, voice calls or emails, or things that involve the transmission of individual packets, nothing more than a single packet, for example, a short email. And then there are, of course, traffic models that are much more complex, that involve, let's say, a series of sequences of packets that constitute a particular message or file. So traffic models then can be based on the arrival of single traffic entities, such as a voice call or a data packet, or they can also be based on much more complicated types of successive demands for service. So let's take a look now at some of these details. In particular, let's look at a point process. And the point process traffic model is one where something occurs that says, I need a service. For example, when you pick up the telephone or you hit the send button on your email server, you create at that particular moment in time a demand for service. And so these points in time are randomly dispersed throughout an interval of time. And so we can say, for example, then a point process consists of a sequence of time instants, T1, T2, T3, and so on, corresponding to the arrival of a traffic entity or a service demand. And so now the point process is well known in the theory of stochastic processes, and it is usually described as what we call a counting process. For example, you sit at a particular central office in the telephone network, and you start counting the number of people who pick up the phone starting at 8 a.m. And you count until you get to 9 a.m. And so at 8:01, somebody picked up the phone. And then at 8:03, another person picked up the phone. And then at 8:06 and 30 seconds, another person picked up the phone, and so on and so forth. And so you keep counting up the number of calls from 1 to 2 to 3 to 4, and so on and so forth. And this is now an arrival process that's a point process or something called a counting process, indicating the number of arrivals in a given time interval, or possibly as an inter-arrival time process where you measure not the number of arrivals you get, but you measure the time between successive arrivals. So these counting processes then are one model for getting a handle on the statistical distribution of traffic demands that are individual events, individual accounts. And so these counting processes then are stochastic processes where n of t denotes the number of traffic entities arriving in a particular time interval, 0 to t. So you could have, in the case of a phone call business, you start counting time and you count for a particular minute or an hour or whatever the case may be, and you count how many arrivals you got, how many phone call demands you got in that particular interval. And then the inter-arrival process, the time between successive arrivals, is also a non-negative random process and measures the separation of individual arrivals. So we can now look at a point process as a stochastic process in terms of the points where arrivals occur in time, or in terms of the time between successive arrivals, one or the other. And these so-called counting processes are well known in stochastic process theory. Here's now a graph that I pulled out of some telephone company publication, and it looks at the distribution of conversation times, 512 customer dialed voice calls. So you have here a measure that says the proportion is longer than a particular time t, and t is the conversation time in minutes. So you see here that the conversation being longer than, let's say, 0.8 minutes over here, okay, is something like, sorry, I mistaken. The probability or the percentage of conversations that are longer than 2 minutes, okay, is about 80%. Okay. The percentage of conversations that are longer than 8 minutes is about 25% or something like that. So this is an example of how the phone company measures the duration of conversation times based on a particular collection of customers and dialed voice calls. Here's now the fluctuation of the number of calls